Earth, the Voyager 1 spacecraft sent back pictures of man's closest look yet at the ring planet Saturn. The closest encounter of spacecraft and planet occurs later tonight when Voyager sails just 77,000 miles from Saturn's yellow clouds. But already one scientist said, in the strange world of Saturn's rings, the bizarre has become commonplace.
The closer that Voyager got to Saturn, the more and more detail and structure Saturn's rings turned out to have. And this just was an enormous surprise to everybody. The rings were simultaneously breathtaking but completely baffling. And there was just far more structure than people had anticipated. Not only did we find many, many concentric features within the rings, but we found eccentric rings. We found that the F ring, which had been discovered by Pioneer, had braids in it and kinks and clumps, all these things no one had ever even dreamed about before Voyager got to Saturn. And then, of course, there were the spokes that Voyager discovered about a month or a month and a half before encounter. And these are these radial features in the B ring that come and go. They are seen orbiting around the rings, and no one had a clue, or at least not a reasonable clue in the beginning as to what caused these features or even what they were. That if you look at the rings of Saturn for a period of time and watch the spokes go around and around, and you examine the appearance of the spokes on the rings, that appearance changes, and it changes with a period that is equal to the period of the spin of Saturn's magnetic field.
Voyager found that Saturn's magnetic field, as Pioneer 11 had already told us, is weaker. That is, it's only about 1/20th the strength of Jupiter's magnetic field. That means its magnetic field doesn't extend as far from the planet, about 1,000,000 miles from the planet. What Voyager discovered was how rapidly that magnetic field was rotating. The magnetic field at Jupiter rotates with a period just under 10 hours. At Saturn, it turns out, the magnetic field rotates with a period of about 10 hours and 40 minutes. So this was the first measure of the length of the day on Saturn.
Turns out, when we finally measured the magnetic field and the radio emissions that are tied to the magnetic field, that the inside of Saturn is moving quite slowly. Well, it's moving more slowly than most of the storms in the atmosphere. And the difference in those speeds translates to 500 meters per second for the winds, which is over 1,000 miles an hour. And that made Saturn a lot windier planet than Jupiter. And that was the big surprise for me when Voyager got there.
Voyager 1 approached Saturn in such a way that it flew past Titan before its closest approach to Saturn. That trajectory then, because of the tilt of the satellite system around Saturn, caused the spacecraft to fly low initially and then get deflected as it made its closest approach to Saturn, going through the ring plane up out of the plane of the ecliptic.
We knew that Titan had an atmosphere. We had no idea how deep it was or what it was made out of. And what Voyager found was a nitrogen atmosphere with traces of methane and other hydrocarbons. And it turned out to be quite a deep atmosphere.
We suspect there might be an ocean of material called ethane. There could be all kinds of complicated hydrocarbons of different colors and different states, some ices, some fluids. There's all manner of hallucination about hydrocarbon goop that rains out of the atmosphere and falls on the surface. As a matter of fact, Titan remains one of the really exciting challenges for future exploration. In the case of Mimas, we see a crater on Mimas that's about 40% of its diameter. A little larger, and that would have been enough to shatter the object. And of course, we wouldn't see the crater then, because it would reassemble like a kind of a giant ball of sand. And in the case of Tethys, there's another very large crater, even larger than the one on Mimas. But in that case, notice the floor is now rounded out so that it is curved as the rest of the object's limb is. In the case of Dione, you'll notice that most of the surface is pretty bland. And only in this one region near the trailing hemisphere do we see a lot of detail on the surface. Here we see a lot of crisscrossing faults with wispy bright markings around them. Finally, we look at Enceladus. We're talking about very cold regions. And here we are with this little tiny object showing geologic activity of the scale that Enceladus does, in which the ancient crater terrain has been broken and has collapsed into the interior. Fluids have flowed out into those open gashes in the crust repeatedly.
Yes, affirmative. I can see a X-ray band shown.
Well, after we got Voyager 1 to Saturn, we went back to NASA and said, we have now satisfied all of the objectives for the MJS for the Voyager mission. How about giving us money and giving us permission to target Voyager 2, to tweak its trajectory just a little bit so that we can go on to Uranus. Now, there was a penalty for this. The data that we got, the quality of the mission at Saturn was a little bit less if we targeted for Uranus than it would be if we optimized for Saturn. And we bared all those facts to NASA. We told them that it was maybe a 60–70% chance, but we thought it was worth it. And I guess we were pretty persuasive because they bought the idea. Soon after Voyager 2's closest approach to Saturn, in fact, while it was behind the planet, its scan platform got stuck. It had a mechanical failure, and we weren't able to aim the cameras and the other pointable instruments on the spacecraft at the targets. After several years, we concluded that, in fact, during the Saturn encounter, we had moved this platform too much, too fast, and that if we used the platform in a consistently at a slower rate, and if we constrained the total amount of angular motion that we applied to the platform, then in fact we would be in a pretty safe condition.
Voyager 2, the amazing robot spacecraft that was launched 8.5 years ago and just kept on going, passed yet another milestone today as it became the first spacecraft to fly past the planet Uranus.
Uranus is not a very photogenic place. It looks more or less like a big blue ping pong ball. But we did see clouds in the atmosphere of Uranus, and they did tell us something. In fact, Uranus is a tipped-over version of Jupiter and Saturn. The cloud patterns are more muted, but they have the same kind of banded structure that Jupiter and Saturn have. Now, what that says is that the spin of a planet is the all-important process or thing that organizes weather.
Uranus is a very peculiar planet in the sense it's tipped on its side right now with the south polar region pointed at the sun. We had expected that the magnetic field pole would also be up near the rotational axis, so the magnetic field would be tipped on its side. What we found was, to everyone's surprise, that the magnetic field, rather than being pointed at the sun, was tilted some 60 degrees from the rotation axis. Not only that, but the center of the magnetic field was displaced from the center of the planet by almost a third of the radius of the planet. Uranus's magnetic field is a bit stronger than that on Saturn, and it extends some 300,000 miles from the planet. The rotation period, that is the length of the day on Uranus, is measured by how rapidly the magnetic field is rotating, is about 17.25 hours.
The big problem going on to Uranus is that it's twice as far away from the Earth as Saturn is. In order to compensate for the darker environment, we had to make sure that the spacecraft would be steadier. And to make the spacecraft steadier, we had to deal with the things that made the spacecraft move while it was just flying through space.
The Uranian rings are inherently dark. In fact, they are no brighter than coal dust. So imagine trying to take an image of coal dust at twilight, but it's even worse than that. So